Hello, welcome to Pipeline Integrity, Gamma Exponent Model Validation Part 1. My name is Colin Scott. I'm a pipeline integrity engineer based in Calgary, Alberta, up in Canada. Today's topic is going to be the Gamma Exponent Model Validation for axial surface cracks. Those of you that have seen my previous video series, Pipeline Integrity, Things That Make Me Go, will probably have seen a little bit of this before. We're going to build on what we saw before, though. So here's a gamma exponent model, which I've nicknamed the GEM. You'll see that it has a very similar mathematical form to the original log-secant model that was developed by the NG18 committee at the Battelle Institute in Columbus, Ohio, back in the early 1970s. However, the NG18 equations tend to be mathematically based on length. In the development of the GEM, I've focused all of the effort on looking at depth, and that makes a big difference. So when we look at the model, we have a remaining strength, which is the predicted failure strength over the flow strength. We have a 1 minus a over t term, so that's the remaining ligament to the power of the exponent gamma. We've got a 2 over pi term, arc cos exponential, k squared is the material toughness. We have 10 factor in there, a is the depth, and a flow strength. Now, the gamma exponent for crack-like flaws is defined as the minimum of the crack length divided by the radius of the pipe, and that's limited to a maximum value of 1. Now, there's fine print in this model. Essentially, the derivation is a flat plate solution, so it's limited to thin wall pipe. I've gone with sort of an arbitrary value of d over t of greater than 20. The flow strength I've used for all my validation effort is the yield strength plus 69 megapascals or 10 ksi. I have not messed around with the various flow strength definitions that are available. The flaw depth can be modified by a pi over 4 term if you want to simulate a semi-elliptical profile. So I'll do that whenever I have, for example, a fatigue crack, or if I have a stress corrosion crack that's likely to have a thumbnail type profile. I have a level 2, I'll call it the ELM algorithm, that can be used if you've got a full flaw profile. Now, I've only validated that on the metal loss flaws to date, and so be careful if you ever want to try using that for cracks. I can also modify my flaw depth by a value of 0.63 or 0.84 to account for stress corrosion crack shielding effects. Those are values that I've determined through looking at classical stress intensity factor solutions. I'm actually looking at putting together another video to explain exactly how that works. Now, I use a 0.63 if I'm looking at predicting hydro tests during a field test, or I'll use a 0.84 if I'm concerned with service failures. I mentioned before that the gamma exponent for crack-like is limited to 1, but if I'm ever doing any metal loss work, I limit to 1/2. You'll see that in, I think, video number 3 gets into that a little bit more. The K-mat used for validation is the lower bound Wall&J-Sharpie correlation, or if you're working with a CTOD, you can use the J is equal to M delta times yield strength, with M equals 2 for plane strain conditions. The Sharpie over area is not recommended. If you see one of my previous videos, Pipeline Integrity, Things That Make Me Go, video number 4, I demonstrate that I believe that Sharpie over area correlation was done under plane stress conditions, which is not, strictly speaking, correct for plane strain conditions that we're looking at in this video. I've done some validation to circumferential flaws, which have been tested under bending conditions, and I've developed a bending correction factor. You can see that in video number 4. That's a work in progress. And I'll say right now that the GEM is not recommended for cold welds or grooving corrosion. It's a little tricky to find consistent data on that matter. I do have some cold weld data, but unfortunately there don't seem to be any toughnesses available for the actual bond line, and that makes the predictions quite difficult. So the first set of industry failure data we'll look at is what I'll nickname the Battelle data, and this was published in 1973 ASTM, failure stress levels of flaws in pressurized cylinders. And this paper contains 48 data sets for surface breaking cracks. Unfortunately, they're not complete. There were a few data sets that did not include toughness values. So what I've done is I've assumed a Sharpie value of 34 joules, which is equivalent to 25 foot-pounds, and I've used that value. That value was actually recommended by Kiefner in a report for PHMSA in 2004. Now, some of you will have seen this before. When I do the validation plot, I look at the predicted failure strength on the y-axis and the measured failure strength on the x-axis. And ideally, all of the data points fall along that diagonal line, which would indicate perfect agreement. They don't fall along the line perfectly, but it seems that the non-conservative data points on the top half of the line pretty much offset the overly conservative data points on the bottom part of the line, and we get a slope, trend line slope of y equals 0.98x. So that means that overall, on average, the GEM model seems to be about 2%, a little bit overly conservative. And I think that in the great scheme of things, that's pretty good. Now, if I go and look at more laboratory data, I can scrounge through all the papers and find work from Eibner, Geilen, Kuzer, and Sturm, Manucci et al., Hosseini et al., and I can dig up various other laboratory data. And when I say laboratory data, I mean these are not real natural flaws, these are machined flaws. And so it's somewhat artificial, but these data points are very, very good for doing model validation such as this. Now, some of you that are in the business will probably look at this list and ask me where is the Keller data and where is the Reyna and Rawls data and things like that. I know that there is other data available that could potentially be used, but my feeling is that those data sets are not appropriate because they're not using pipeline steels. They're using various heavily alloyed steels that are used for pressure vessel situations. I don't think that those are suitable to be put into a pipeline model. You're going to have different work hardening properties, different behavior potentially, and I've seen in some other work that those data points come out as overly conservative, and I don't want overly conservative data points to be pulling my model in the wrong direction. I don't think that's appropriate for the overall reliability of pipelines. Now, if I take those data points and line them up just like I did before, we have a predicted failure strength over the true measured failure strength. And in this case, we see that this data set is a little bit overly conservative. You see that the trend line falls below the diagonal. The trend line slope there of y equals 0.90x indicates that the model for these data points is about 10% overly conservative. Not horrible, but I would like to do a little bit better. When we switch from machined flaws to real flaws, I rely on work by Kiefner and Kolovich. They put together a massive study where they looked at ERW and flash weld seam failures. And that was work that was done for the U.S. Department of Transport in September of 2012. They do have a good listing of fatigue cracks and a good listing of hook cracks. And what I've done is I've looked at the lengths and depths that are reported, the material properties, the toughness that's reported, and the failure pressures. And I've done a very similar validation study using the GEM. Now, I will tell you that for the fatigue cracks, I have included a pi/4 factor applied to the crack depth, and that's to simulate having a semi-elliptical flaw. And that's pretty typical in this sort of business. However, with the hook cracks, I've not included that pi/4 factor. Hook cracks tend to be straighter, and so I've just left the depth as it is, and that's essentially simulating a rectangular crack. So first of all, we'll look at the fatigue cracks. You'll find that the overall accuracy is pretty much right on the money, maybe a tiny bit overly conservative. What you notice here is that there's a lot more spread in the data, and that's really just the nature of the beast when you're dealing with natural flaws that have funky shapes, or you may have a little bit of residual stress acting near the weld. There might be some peaking or weld mismatch that makes your numbers go off a little bit. In the great scheme of things, that precision is not horrible. Obviously, I would like to have those data points a lot tighter to the line, but well, them's the breaks. Here, when I look at the hook flaws, I get a very similar situation. I've got one quite non-conservative data point, which I'm not too pleased with, but the rest of the data points seem to be behaving fairly well in the great scheme of things. Those of you that deal with hook cracks out there know that they are notorious beasts, and the fact that this model is showing pretty reasonable agreement gives me a lot of confidence that the gem model overall is doing quite well for itself. Now, if we look at some very simple statistics, what I like to do is I like to look at the failure ratio, which I define as the true failure strength divided by the predicted failure strength. And if I take the mean of all the data points, I can come up with an accuracy, or an estimate of accuracy. Now, in the case of the machined laboratory crack-like flaws, I find an accuracy of 1.06, which means that overall the model is about 6% overly conservative. That's not too bad. And the precision I'm using is basically the standard deviation of those failure ratios, and I get to 19%. So that's where we are with the machined laboratory cracks. And then if we go to the X-service pipeline crack-like flaws, the fatigue and hook, we've actually got a pretty good accuracy of 1.01, meaning we're pretty much right on the money. But in that case, we lose something in precision. The standard deviation on that data set was 22%, meaning that we've got a little bit less confidence in our gem predictions there. In the great scheme of things, though, these numbers match up fairly well with other models that are available in the market. If I plot everything together, you'll see that the behavior of these data points is pretty reasonable. Now, if you're interested in further viewing, I'd like to suggest that you take a look at my other video series. It's called Pipeline Integrity, Things That Make Me Go, And that's 6 parts. Each part is about 10 or 15 minutes. And that video series is a critique of the NG18 based assessments for both corrosion and cracking. If you look into the mathematics of those NG18 based equations, they mathematically focus failure pressure predictions on the flaw length. And that's really not correct. Everything should be based on the flaw depth. So I go through a mathematical exercise where I demonstrate why that's a problem and what the ramifications of it are. I'd also like to recommend that you take a look at the other 5 parts of this video series, where I'm looking at validation of this new gamma exponent model using several other flaw types, including axial stress corrosion cracking. We've got some corrosion or metal loss, circumferential surface cracks, and axial through wall cracks for leak rupture boundary analysis. And you can find those all through YouTube, so please help yourself. If you're not much for viewing, but you'd rather read, I do have 3 technical publications that are, well, peer-reviewed and out there for real. If you're interested in the derivation of the gamma exponent model and you like to play with math, I would suggest the paper number 3 here. It's ASME Journal of Pressure Vessel Technology. That goes through all the mathematics that were necessary to derive this model. If you've made it this far, thank you very much for your attention. I think that the gamma exponent model is validating fairly well at this point. Hopefully you'll agree with me, and hopefully you'll take the time to look through some of the other videos to see that the model works quite well for other flaw types as well. Until next time, thank you for your time.